Moving on to the energy portion of the practice test, let's go ahead and solve. So a 2 kilogram mass is lifted 4 meters above the ground. We're going to find the change in gravitational energy as Eg equals m times g times h. That'll be 2 times the acceleration due to gravity, which is 10, times 4 meters, and that is going to give us 80 joules of energy. A large moving toy car has 40 joules of kinetic energy. We have its mass, and we want to know how fast it's going. Well, we know that Ek is 1/2 mv squared. So we put in our numbers. 40 equals 1/2 times 10 times v squared. So that means v squared is going to end up equaling 8. And so when we simplify, we're going to get v equals 2.8 meters per second. Now, number 13, all we have to do is compare kinetic energies. Now we say how many times greater. Let's get a ratio then. So a car has an original kinetic energy equal to 1/2 times, well, we don't have a mass, so let's leave it as m. And that's situation 1. And situation 2, we can do Ek of 2 is 1/2 times m times 20 squared. So what we can do is we can actually divide these two numbers, 1/2 m times 400 when we square 20, divided by 1/2 times m times 100. And look what happens. The 1/2s cancel, the m's cancel, and so we actually get a ratio of 4:1. So it's a 4:1 ratio. And yes, I want to see ratios in the most reduced form possible. All right, number 14, we have a box where you have a situation where a box is in a compressed spring, and then it's launched with a speed, and we want to find the energy stored in the spring. So this is a little different than the pre-lab problem that we did. And this is what we'll say. We note here that Ek is 0, and we also note that there's no gravitational energy to start with because there's no height. Again, that's because V is 0, and here we have H is 0, so we only have EE. And in the end here, there is no E elastic, there is no gravitational because there is no height. We see that it's moving, and we're told that it's frictionless, so there's no dissipated energy. So let's begin by getting the energy stored in the spring in the following manner. E elastic equals E kinetic. And let's just plug in what we have. So we have E elastic equals the E kinetic, which is 1/2 mv squared, and we can put in our numbers right here. Remember, we're not asking for the compression of the spring yet. We're simply saying what's the energy stored in the spring. So we're going to say E elastic. The E elastic that was all stored here turns into E kinetic in the end of the problem. So that's why we can use 1/2 mv squared to solve for the E elastic, because all this E elastic became kinetic energy. So I'll say E elastic equals 1/2 times the m, which is 8, times v squared, which is 10 squared. And so I'm getting 400 joules worth of energy. Now, in this initial situation, the spring was compressed 4 meters, so let's find the spring constant. All right, so now we can use E elastic equals 1/2 kx squared to get the spring constant. So that'll be 400 equals 1/2 times k times 4 squared. Simplifying further, we're going to get that 800 divided by 4 squared equals k. And that's going to give us a spring constant of 50 newtons per meter.